500 kilometers of highway slice directly through the shifting sands of the Taklamakan Desert. Why attempt to build in a location known as the Sea of Death? The wind here is capable of burying an entire convoy in just one night, but the goal was to tame this landscape, regardless of the natural resistance. One can notice how the endless dunes loom over the path, threatening to reclaim the space. The construction cut straight through the Golden Hell, but realizing this steel miracle demanded immense capital. The Xi Jinping government invested nearly $3 billion to support the logistics. But this is just the beginning of the challenge. It is visible how heat waves rise from the ground, with temperatures reaching 70 degrees Celsius. Tens of thousands of workers labored under these conditions, battling blinding dust storms. Sand drifts ceaselessly across the work zones. It seems simple to lay asphalt, but in reality, even a small mistake would allow the dunes to swallow the entire road. Thus, the engineering feat stands firm against the elements. 70 degrees Celsius is the scorching temperature the surface reaches in the heart of the Taklamakan Desert. Located in the far west of China between two towering mountain ranges, this endless ocean of sand dominates the Xinjiang region. Before the highway existed, crossing this terrain meant walking for weeks or even months through one of the harshest environments on Earth. Sandstorms here can swallow entire convoys in just minutes, burying them under waves of dust. But this is just the beginning of the challenge. Yet, beneath this hostile sea of sand lies a hidden treasure of immense value. Because the desert conceals enormous reserves of oil, natural gas, coal, and rare earth minerals, Beijing faced a critical strategic necessity. These resources are vital for strengthening the nation's global position, requiring a reliable link to extract and transport them to the rest of the country. To achieve this, engineers attempted the unthinkable operation of bridging the void. They initiated the construction of the Luntai-Mingfeng Expressway, a project stretching more than 522 kilometers. Work began in 2017 and concluded in 2021, establishing China's first and longest desert crossing highway. At first glance, laying a road seems standard, but in reality, building on sand that never stops moving was once deemed an impossible engineering blind spot. One can notice how the dunes constantly migrate, threatening to consume any static structure. How do you build a permanent highway across a desert that flows like water? The solution requires comprehensive data before a single layer of asphalt is laid. Survey teams utilized high-resolution satellite imagery combined with ground-penetrating radar to pierce the surface. They conducted thousands of wind measurements to map the complex migration patterns of shifting dunes. This rigorous analysis allowed them to identify isolated pockets of stable ground amidst the chaos. The path is thus defined, allowing the construction teams to advance into the sands. 30 meters is the depth reached by drills in the Taklamakan. Survey teams lived here for months, boring hundreds of holes to study hidden layers. Why go so deep? The sand looks solid, but the subsurface must be verified to support the load. One can notice the rigs working, but this is just the beginning. Every marker is staked by hand. It looks outwardly simple, but in reality, positions are logged with centimeter-level precision. One can notice how the route connects the Tarim Basin's oil fields. It gets more complex further on, because the road must avoid wind corridors where sandstorms bury infrastructure overnight. Therefore, the path curves. It is visible how the stakes guide the way. This turns a blank white void into a black ribbon of pavement. The survey paves the way for construction. 60 degrees Celsius is the temperature the air reaches above the desert floor, heat intense enough to bend metal structures. Before any concrete was poured or asphalt rolled, the project began with an unexpectedly low-tech mission to anchor the sand. Why recruit hundreds of local farmers from small oasis villages instead of using advanced machinery? Modern engineering usually relies on heavy steel equipment, But without this manual defense, the shifting dunes would swallow any heavy vehicle attempting to enter the site. Men and women earning between $80 and $100 a month, a humble income that kept their families afloat, took on the job. They tied bundles of straw, twigs, and thin bamboo into long sheaves. Teams of a dozen workers drove these organic stakes deep into the dunes, forming a vast checkerboard pattern. Construction norms required that each square measure exactly 1 meter by 1 meter. One can notice how the bundles were laid diagonally at 45 degrees to deflect the wind and trap sand inside the grid. The workers wrapped their faces in cloth and soaked their hats with water to endure the scorched environment. They worked in silence against the relentless wind to secure the ground. Within months, the transformation became visible across the landscape. More than 1,000 hectares of straw grids pinned the dunes in place. Wind velocity near the ground dropped by 40%. The sand began to crust and harden, allowing heavy trucks to cross without sinking for the first time. These checkerboards created new zones of life, protecting nearby villages and giving native desert plants a foothold again. From this quiet labor rose the first layer of an engineering triumph. But this is just the beginning. On this anchored sand, the construction of the Taklamakan Desert Highway could finally commence. Hundreds of bulldozers were deployed to reshape the terrain by flattening the dunes. They cut down high ridges and redistributed the sand into lower areas to create a balanced surface. Surveyors checked elevation and slope with precision instruments to ensure uniformity across miles of open desert. Conveyor systems pushed excess sand away from the work zone. At first glance, moving sand seems simple, but in reality, the surface must be strong enough to support construction machinery without the risk of collapse. Compactors gently press the top layer to form a firm and workable foundation. It gets more complex further on. Engineers discovered that injecting water into the loose surface helped bind the grains together. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site. Moisture penetrated several inches deep, creating a denser and more cohesive layer. It is visible how the heavy rollers move in once the sand reaches the right level of dampness. The steel drums turn soft, shifting sand into a firm, uniform base. The constant rumble echoed across the desert as each pass removed air pockets and locked the particles in place. By the time the surface dried under the sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks, forming a solid foundation built from nothing but sand and water. Workers began spreading a base layer of soil over the stabilized sand. Loads of reddish earth poured from dump trucks, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted to support the next stages of construction. Beneath the desert highway, the foundation had to be rebuilt from the inside out. The Taklamakan sand was fine and dry, unable to bear the weight of even a single truck. Engineers drove sand compaction piles and mixed cement directly into the soil, creating dense vertical columns that acted like roots beneath the road. In looser areas, strong synthetic nets known as geogrid mats were laid down to spread the load evenly. Once reinforced, convoys of dump trucks arrived, pouring crushed stone and grated gravel across the route. Bulldozers spread the mix into layers 20 to 30 centimeters thick, followed by vibratory rollers pressing it into a solid platform. By the end of this stage, the pale gray subgrade stretched like a giant runway through the dunes, waiting for its black asphalt skin. (170°C) is the critical temperature reached by the heating of stone, sand, and polymer-modified bitumen inside portable asphalt plants. These stations roar to life at the very edge of the desert, preparing the mixture for a giant runway stretching through the dunes. Insulated tankers deliver the hot mix non-stop to paving machines waiting on site. Each paver spreads the glowing asphalt in layers about 6 centimeters thick, while steel rollers follow close behind to compact the material before it can cool. But this is just the beginning. Why do the final passes switch to rubber tire rollers instead of heavy steel drums? At this stage, the surface requires a delicate finish to seal tiny air gaps. The rubber tires create a smoother texture, which effectively prevents future moisture intrusion and cracks. At first glance, rolling seems like a simple mechanical compression, but in reality, it is a thermal race against time monitored by sensors. If the asphalt temperature drops below 140 degrees Celsius, the machinery stops immediately. Otherwise, structural defects would inevitably form once the material cooled. Supervisors check flatness with laser beams, allowing no more than 3 millimeters of deviation per meter. The surface hardens into a flawless black sheet, capable of withstanding temperature swings from -25 to +70 degrees Celsius. It gets more complex further on. Workers spray a protective seal coat to give the surface a deep shine and lock out moisture. One can notice how the newly paved highway gleams like a dark mirror under the sinking sun. What was once an empty wasteland now reflects the light of progress born from steel and human endurance. After 4 grueling years, the 4-lane highway cutting across China's largest desert stands complete. But the story did not end there, as the engineering achievement was so remarkable that even seasoned American engineers acknowledged the scale of the project. What came next left international experts even more astonished. A project on an even grander scale began stretching boldly across the same unforgiving sands of the Taklamakan. The Hutan-Rokyong Railway extends 825 kilometers as part of the larger Taklamakan Desert Loop Railway. Transition to the next level, the full loop spans more than 2,712 kilometers, with construction on the southern rim concluding in June 2022. This line holds the title of the longest desert crossing railway in the world. More than 65% of the route, totaling over 500 kilometers, rests on elevated concrete viaducts supported by more than 11,000 pillars. This design allows desert winds to pass freely underneath, preventing sand from burying the tracks. Once the ground base was stabilized, workers began the arduous task of erecting bridge pillars. They drilled through dozens of feet of loose sand to reach solid gravel or compact soil. And this is not the limit. Reinforced concrete pile drivers operated day and night using steel casing pipes. One can notice the flow of bentonite slurry used to keep the boreholes from collapsing during the drilling process. Concrete was poured from the bottom up through tremie pipes to prevent air pockets, while steel cages were positioned with millimeter precision. Even the slightest misalignment could cause the pile to tilt, because daytime and nighttime temperatures differed by more than 130 degrees Fahrenheit. Construction crews worked mostly at night when the wind was calm and sandstorms eased. Thanks to these piles, the railway's foundations seemed to grow roots deep into the desert. Everything only gets more complicated. 11,000 bridge piers began to rise row after row, forming a vast concrete forest stretching across the dunes. Each pier stood between 16 and 50 feet tall, cast using slip-form molds, reinforced with galvanized steel and salt-resistant additives. This protection is necessary to withstand the desert's corrosive climate. The short, uniform spans between piers were designed to minimize the effects of wind and extreme temperature changes. As the sun set behind the Kunlun Mountains, the endless lines of pillars stretched toward the horizon like a skeleton of steel. On top of the pier caps, heavy crawler cranes and self-launching gantries lifted thousands of pre-stressed concrete box girders into place. Each girder measured over 100 feet long and weighed several hundred tons. Specialized flatbed rail cars transported them for hoisting one by one. Engineers aligned the girders with laser precision, keeping tolerances within just a few millimeters. It does not end at this stage. Crews poured the bridge deck slabs or installed precast concrete panels to form a smooth surface for the tracks. Every span was spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. More than 65% of the Houghton-Rokyong Railway, about 310 miles, runs on these elevated viaducts. From above, the railway appears like a silver ribbon cutting across an ocean of gold. Concrete blocks known as sleepers are placed evenly along the track bed to distribute the weight of passing trains. But the process is only gaining momentum. Workers align each sleeper precisely, then use a lifting frame to lower the rails onto them. Once fixed and fastened, they keep the track straight and stable, preventing it from bending or shifting under heavy loads. After the sleepers were secured, crews began laying the steel rails on top. Each rail, stretching more than 260 feet long, was lifted into place by specialized cranes and carefully aligned along the center line. Workers adjusted every joint and gap to allow smooth expansion under heat, then tightened the fastening clips that locked the rails onto the concrete base. It took 11 months of continuous work to complete the hundreds of miles of track stretching across the desert. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement, vibration, rail temperature, and wind-induced sway. The bridges were load-tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters even after hundreds of test runs. And this is not the limit. Thanks to the elevated design and natural airflow beneath the viaducts, no sand accumulated on the tracks. All operational data flowed to the control center through sensors and solar-powered cameras that monitored every section in real time. After 6 months of rigorous testing, the railway officially opened in June 2022. Thus, the loop circling the Taklamakan Desert was finally closed, marking the end of this colossal construction effort. One single loop binds the perimeter. Why circle the Taklamakan Desert? At first glance, it seems indirect. But in reality, the ring stabilizes the route through China's largest desert. It is visible how the dust settles. The building process is complete.